Any questions? Okay, let's move on to the quiz. Let me share. Okay, so here's the quiz. And question 1 is for each of the following, determine if it converges. I should say if, sorry about that, or diverges. Show your work and state what theorem you were using to make your conclusion. Okay, so we have this first one, which is a summation n equals 0 to infinity of 1 over n plus 1 plus cosine of n. So in all of these convergence divergence questions, the very first step is always to come up with a strategy. Okay, so you think about what test might be appropriate. We don't have that many yet, but we will pretty soon. What is the test that might be the most appropriate for this particular series? What do you guys think?
Integral test?
We could try the integral test, but there's a problem with the integral test. What's the problem? What do you have to have for the integral test to work? Do you remember? There's a condition you need.
It has to be positive, decreasing, and
exactly, it has to be positive, and it has to be decreasing. This is neither, right? I think you all know cosine is not just a positive number. 1 over n plus 1 is very small. If you add cosine of something, you're going to get a negative number for a lot of n's. Is that clear? So if n is even 6, I believe, you get a negative number. So this one, the integral test will not work on this one because it's not positive. It's also not decreasing. Okay, it's certainly not geometric series. I hope you all look at this and say this is not a geometric series. What's the other test we've got? Starts with a D.
Divergence test.
The divergence test. So on this one, and I copied them over here. We're going to take a limit. And I wonder if it'll let me do this. Gosh. Yeah. That way I can take a limit of and just get rid of what I want to get rid of. So instead of a sum, we're going to take a limit. Okay, and I'll just assume that means n goes to infinity. What is that limit? Look at the first term. Where does the first term go if n goes to infinity? 0. What about the second? What is the cosine of infinity?
Indeterminate.
Indeterminate. This is equal to d and e, right? Since, oops, this equals d and e, since the cosine of n oscillates. So therefore, okay, if the limit does not exist, what can we say about the series itself?
It diverges.
Exactly, the series diverges. By the divergence test. I'll try div test. Any questions on part A? Any questions? Okay, what about part B? We're going to get strategy now. So what test can you use for part B?
You'd use the integral, or
you could do the integral, but I like Victor's idea better, P-series test. P-series is a lot faster. So notice that P is equal to 1/2. Okay, what's important about the number 1/2?
1.
It's less than
It's less than 1, less than or equal to 1. So it's less than or equal to 1. So by the p-series test, that's PST. What can we say about the series? Series
That
divergent.
it's divergent.
Okay. Any questions on part A or part B? Okay, one of the things that could be frustrating too about these, if you know what to do, it's really easy. And that's frustrating because then you see it done, you weren't able to get it, and you're like, oh, that was easy. What was I thinking? You got the only way to get good at this is practice. Okay, watching me isn't enough. You need to really practice. All right, part C. Okay, what test can we use on this one? Again, we're going
Integral
for
test.
yeah. Notice that just visually, this thing goes to 0, which you got to do for the integral test anyway. So notice the limit goes to 0. Right, since the denominator is larger or has a larger power than the numerator. Okay. Also notice that the dominant terms right for large N are 2n over n to the 8th. Is that clear? So this decreases. It's a decreasing sequence for large N. Okay, therefore we can use the integral test. Okay, you have to check those two things first to be able to use the integral test. Okay, otherwise you can get in all kinds of trouble. For example, part A, you can't use the integral test because it doesn't go to 0, it's not decreasing, it just doesn't work. B, you can, but the P series is easier if you can. Any questions so far on part C? Okay, so now, okay, I tried to make this not too bad. But I'm going to copy it so that I can get into the equation editor and then adjust. So now let's go ahead and integrate. So now we're going to have an integral. From 1 to infinity. And the ends become x's. So 2x plus 1 over x squared plus x plus 7 to the 4th dx. Okay, I tried to make this nice. Why is this nice?
Because its integral is fairly easy.
Yeah, but in particular, why is it easy? What makes this easy?
The power of 4 at the bottom, it kind of like let.
Not the 4. 4 has nothing to do with the 4, actually.
Really? Oh.
Yeah, I like
Oh,
Victor's
you're
idea.
so-
U sub. The derivative of x squared plus x plus 7 is 2x plus 1. Is that clear?
Yeah.
Yeah. So that's the reason why this is easy, is that because the derivative of the inside is the top. Otherwise, this is a mess, right? The 4 has nothing to do with it. If it had been x squared plus 3x plus 7, this is not fun at all. Okay. Maybe you had fun last quarter and loved inverse trig substitution, but I don't think it's very fun at all. Okay, so but because of the U substitution, let's just do it. I'm not going to write out the U substitution. That was last quarter. Now I'm assuming you just know how to do it. Okay, and that's in the basic, yeah. So that's equal to the integral from, notice if u is x squared plus x plus 7 and x is 1, then u is 9. And if x goes to infinity, then u also goes to infinity. Oops. There we go. So we can go from 9 to infinity, and this just becomes u to the -4 to u. Isn't that pretty? And that's just equal to, again, the integral of u to the -4 is -1/3 u to u to the -3rd. And that, let me do that. No, won't let me do that. That. From 9 to infinity. And the important thing is what happens when I plug in infinity or take a limit as u goes to infinity?
You get 0.
Yeah, we get 0. So this is equal to 0 minus a number. I'm just going to write number because I don't really care what number it is. It's a number. Okay, so in particular, if we get a number, what can we say?
It converges.
Yeah, so the integral converges. So by the integral test, the series converges. Any questions at all on this particular question? Okay, these are very standard. It doesn't make them easy, but you need to practice so you get good at them. Okay, there's not a lot of tricks on this one, but you do have to be able to look at it and know what test to use and how to use it. So for the integral test, there's a step-by-step process. First, you identify integral test might be a good idea. Second, you notice the limit goes to 0. Third, you have to notice that the function is decreasing. Fourth, you take an integral. And then 5 or 5th, you say by the integral test, the series, and if the integral converges, you say converges. The integral diverges, you say diverges. Any questions on the integral test?
I have a question, and it's more related to part A.
So let me scroll up.
Do all trig functions diverge due to oscillation, or just the sine and cosine functions?
If it's just the trig function, then it diverges. Okay, but had it been instead, let's say I just said summation. I'll just do it so you can see it. It's easy to make. That's a good question. It's an important one. So you got to be careful about saying, I see trig, so it must diverge. That doesn't work. Because what if I gave you this one instead? Okay, now we got a trig function, right? Okay, maybe I need to change this one a little bit. Let's start at 1 so we don't have a problem with the denominator. There we go. Okay, so now we have a trig function. All right, this one, it turns out, converges. And what makes it converge is the over end of the 5th. And we're going to learn that today, actually. We'll be able to do that at the end of today. So this converges it does not diverge.
So it entirely depends on orientation then.
if that's the way you're using orientation, yeah, if it's just a trig function by itself, always diverges. So the summation of the secant of n diverges.
Okay.
Right? Because it doesn't go to 0. That's the important thing. It's by the divergence test. Okay. On the other hand, if you have other stuff, all bets are off. Okay. Cosine of n over n to the 5th converges. Cosine of n over n diverges. So it really depends on what you're, what you've got. Does that make sense?
Yeah, thank you.
Yeah, good question though. And again, this is going to lead into what we're doing today, is that we'll be able to prove that this converges today using the limit comparison test. But that's going to be, in another hour or so. All right, let's finish it off. Let's do number 2. So number 2 is use the remainder theorem to come up with an upper bound for the error in using the summation n equals 0 to infinity, 0 to 100 of 1 over n to the 4th to approximate n equals 0 to 100, 0 to infinity of 1 over n to the 4th. You know what? There's an error in that. I don't know if anyone noticed. It should say 1 to 100. I usually don't care about the beginning number. It's really the tail that matters, because that's what we're trying to do. So hopefully that didn't bother anyone. But if it did, I apologize. It should start at 1. Okay, in this case. Okay, so what does the remainder theorem say? Can you remember from this section?
We can integrate and take a limit as n goes to our 100.
Yeah, so n goes to infinity, actually. We're going to take a limit as n goes to infinity. What we're going to do is we're going to integrate from 100 to infinity of 1 over n to the 4th, or 1 over x to the 4th. So let's do that. So we're going to integrate from 100 to infinity of 1 over x to the 4th dx. That's not supposed to be a hard integral, by the way. In fact, we already did this one with a u, same thing. So it's going to be negative 1 over 3 times x to the negative 3. And that's going to go from 100 to infinity. And we've already seen this. If we plug in infinity, what do you get?
0.
0. So that just goes away. And then we have a minus, so that's a plus. We plug in 100. And that's equal to 1 over. And we have still the 3. And then 6 zeros, right? Every time you multiply by 100, you get 2 more zeros. That is the upper bound for the remainder. Don't make it look easy. Okay, so there's nothing to do. You just use the theorem and you integrate from 100 to infinity. Any questions at all? Any questions at all on this quiz? Okay, so just note, by the way, if you do use the, from 0 to 100, that's pretty darn good. Okay, you're not exactly at this sum from 0 to infinity, okay, or from 1 to infinity, let's call it, but you're within 1 over 300,000, and that's good enough for all engineering purposes. So a lot of times, that's the whole point of this, is this helps us decide, have we gone far enough so that we estimate, okay? And by the way, by the p-series test, this converges. So we know it converges, and if we use a computer to do the first 101 terms, or 100 terms, then we're pretty darn good, okay? You've got almost a perfect answer. Any questions on this idea? It's kind of the whole point of the remainder theorem, is in the combination of the remainder theorem and the integral test, we're able to use a computer to get a very strong approximation of a series. And we know how good our approximation is. So any questions at all? Okay, so what I want to do is I want to give you a big reminder. I'm going to pop to the syllabus. What happens next Friday? It's not a holiday, by the way. What happens next Friday? Yeah, presentation. Okay, so next Friday are the presentations. So let me pull down. So by the way, we are here. And next Friday, you'll be doing presentations. Okay, so that's the plan for Friday. Do you all have partners? If you don't, you need to get them. Chat box is a great way of finding partners right now. If you have partners, great. If you don't, get yourself some partners. Okay. Do you remember how big the groups are supposed to be? 2 or 3. What's better, 2 or 3? Okay. So 3 is better if you can, because you have less work to do if there's 3 of you. You have to do 1/3 of the work instead of 1/2 the work. So it's always better to do 3. You can do a 5-minute presentation amongst your group. And I'm here to help, but you have to ask for it. Okay. So you have to go find, you find an application that you're interested in, do a little research, a little study, and then get ready for a 5-minute presentation. Okay. Any questions at all about the application? I figure this is probably a good time to start talking about it since we just had a long holiday. And again, get partners. You need to have a partner. It is an absolute requirement. Okay, you can't be by yourself. And we're not losing any students. That's the good news. So, if you know someone, they're still in the class. Kind of different stats. My stats class is a little ugly in terms of losing students. Okay, so I'm going to give you a moment in the chat box to get yourself partners. Again, if you don't have one, you should have one within the next minute or 2 so that you can do it in your chat box. And if there's only 2 of you and someone asks to be a partner, please accept the person. Okay, it's a nice thing to do and it makes your life easier. Okay, and give you another little bit of time and then I want to get to new material. So, any questions about the application presentations? Okay, and as I mentioned before, you're going to be sharing your desktop. Okay, I'm not. When you do your presentation, so everyone will be able to see what you're presenting on your screen, and you're going to be talking. The group of you will be talking. So you have to decide one person shares the desktop, the others don't. So make sure you coordinate that on who's going to be doing the computer work during the presentation, and then who's talking about what. And everyone should talk at least some. Okay, any questions? Okay, I think I'm going to go to new material. Let's move on. Okay, and just let you know, I'm around. So if you have questions about the presentation, drop me an email or talk to me during the webinar, whatever it is. Office hours are great too. I'll be around office hours and happy to help you out. Okay, so the next thing I want to do is I want to look at an example. Let's suppose we had something like this. let's suppose we had a summation. And by the way, I think just out of laziness or just easiness, so I don't have to waste your time. If I just write sigma, that's going to go off. It means an infinite series from a starting place, could be 0 or 1, whatever, to infinity. Because right now, all we're going to care about is does it converge or diverge. So I don't really care where I start, and it always means infinity. So if I just write sigma in my lecture, that's what I mean. Okay, so hopefully you're okay with that. So let's suppose we have a summation of, let's suppose you had 1 over n to the 5th plus 2n to the 4th plus, how about n squared plus 3. And by the way, what do you think the question is?
Is the series convergent or divergent?
Right, and that's the question of the chapter, basically. So does the series converge? Okay, and that means does it converge or diverge? It's the same question. All right. Well, the limit goes to 0, doesn't it? I hope you can all see that. If n goes to infinity, then the sequence goes to 0. So can I use the divergence test? What do you think? Can I use the divergence test? Okay, definitely not. Okay, you can only use the divergence test when the limit does not go to 0. Limit goes to 0, so the divergence test fails. Is this a geometric series?
I want to say no.
Definitely not. Definitely not. This does not look like a number to a power. Doesn't look anything like it. I hope you all agree with that, right? That was not a trick question. It was an easy question. This is not anything close to geometric series. Okay, this is a harder question. Can you use the integral test? Okay. All right, so I see a yes. So I have an extra credit project for you. You can integrate this one. I'll be very impressed. Okay, good luck. Do you really think you can integrate this puppy? 1 over x to the 5th plus 2x to the 4th plus x squared plus 3 dx. Okay, this doesn't factor, by the way. There's nothing nice about this thing. Doesn't factor, so you can't just use partial fractions and do it that way. There's nothing good about this. Do y'all agree? So the integral test in theory works, but not really because we don't know how to integrate this. So we don't have any tests. We don't have any tests that work. Do you agree? Okay, there's no test that tells us if it converges or diverges. But here's what we can do. Let's use a little logic. And let's say, well, let's think about the dominant terms. What's a dominant term in the numerator? That's easy. That's a dumb question.
1.
1. It's the only term, so of course it's dominant. What's a dominant term in the denominator?
N to the 5th.
N to the 5th. So let's look at a different series. Let's look at the series 1 over. I got to get used to it. This one you have to do fraction, the other one you don't. 1 over n to the 5th. Make it bigger. What can you say about that series?
I think it will converge.
Yeah, I like that, except I don't like the word think. You're supposed to know.
Okay, if we do the integral test, it will converge.
You could do integral, but
Yeah,
what's
piece,
easier?
the exponent's greater than 1, so it's
Yeah, and what's the test called? Because you do have to know the names of the
test.
test. So what is it?
It's convergent.
Yeah, Eduardo said by the P-series test. So you do have to know the names of the test. Because I will always ask you on quizzes and tests and exam to cite what test you're using. So by the P-series test, actually I think I've been saying PST, so let's do that. PST, this series converges since 5 is greater than 1. And that was the P-series test. All right, so that at least gets us something. So we can kind of say, what does it kind of be? What does it look like? And it looks like 1 over n to the 5th. And 1 over n to the 5th converges. Do you all agree? By the P-series test. All right, now we got to think a little bit more. One is that notice that the terms are all positive. Is that clear? So this sequence of partial sums is increasing. Do you agree? So if we keep adding more positive numbers, then you get an increasing sequence. So that means, let me give you another word that might ring a bell, monotonic. Do y'all agree? So we have a monotonic sequence of partial sums. But it's better than that. What else do you want besides monotonic when you're talking about a sequence to decide if a sequence converges or diverges? Do you remember? I know it's been a week, but maybe a week and a half, something like that. Put that in, that might give you a reminder. You remember? Bounded. We'd like it to be monotonic and bounded. Well, the sequence of partial sums is bounded below by 0. Do you all agree with that? If you look at the sequence of partial sums, you never get negative because you're adding a bunch of positive numbers. Is it bounded above by anything? Okay, one more guess, Victor. Yes, one big letter. It's the biggest letter on this page of an English letter. Yeah, it's bounded above by L. And that is because we can say that, and I'm going to do a copy and paste. I don't have to keep writing this. Because that guy is less than 1/n⁵. For all big N. Do you agree with that? If a denominator is larger, then the fraction is smaller. Everyone okay with that? So if every single thing you're adding in your group is smaller than everything that your friend is adding, then guess what? Your friend's answer is always going to be bigger. Do you agree? And that's what this says, is that 1/n⁵ plus 2n⁴ plus n² plus 3 is smaller than 1/n⁵. So if we add up, plug in 1, plug in 2, plug in 3, up to 1,000,000 or something, you're still going to be smaller. Any questions on that? Any questions on that idea? So by, now a little too big. The bounded and monotonic convergence theorem the sequence, and since we have a couple sequences, let me state what I'm talking about. That's our sequence, converges. Any questions on this idea? Any questions on how I was able to come up with this really messy sequence converging by pairing it with a very nice sequence? And that's what today is all about, is what we're going to be doing is we're going to be comparing. We're going to compare one sequence to another sequence to see if it converges or not. Is that clear? Any questions? Okay, so that's an example. Let me give you another example. Let me just pop in a new sequence. So 1/n minus 0.5. Make it look prettier, 0.5. Ah, try that again. Okay, so the question is, does this series converge? Okay, and remember, if I don't put in numbers, and that means n equals some number, who cares, to infinity. All right, well, can we play the same game? Does this look like a series we know about?
Yeah.
What does it look like?
1/n.
In a word. The harmonic series, good. I want you to know that word because that word's important. So it's a harmonic series. I haven't mentioned this. Do you know what you call a harmonic series? So let me ask you something. Do we have anyone who plays any musical instruments?
I play the piano.
Okay, good. When you play the piano, you have keys, right? What happens when you hit a key?
It plays a tone.
What happens when you hit the next key?
It plays a different tone.
And what's the relationship between one tone and the next tone, physics-wise?
Frequency is decreased or increased.
By 1 over n, the harmonic
Really?
series. Yeah.
Oh. Huh.
So there's actually a reason why we call this harmonic series and why you say harmonics. There's some really cool mathematics. I think I'm the only person I've ever met. When I listen to music, I see the equations. Maybe you guys too, but I doubt it. There's some beautiful mathematical equations in music. And harmonics is a big part of it. You don't get infinite series because you don't hit an infinite number of keys, but still you can talk harmonic. So just note that there's a reason for calling it harmonic. It's not a coincidence that you've heard the word harmonic in music. I think you've heard the word harmony, right? Right, it comes from music. Okay, so just for fun, I figured I'd mention, why it is that we even say it. And so when you take a little more advanced physics, you should learn about that. It's really cool. Or differential equations if you take my class. Okay, so let's take a look. We know by the harmonic series test, HST, that the summation of 1 over n, 1 over n. I hope you know, what does it do? Divergence. Right, that's the classic, it's the example of the divergence series. As I mentioned, we're going to be using it and talking about it a lot in this class. So get that one down. So we know that the summation of 1 over n diverges. Okay. So now let's take a look and let's see if we can play a similar game. Okay, so what does that mean? Another way of saying that is that this guy, the summation of 1 over n, equals infinity. Okay. That's kind of what it means to diverge. It means, or the limit goes to infinity is another way of saying equals infinity. All right, well, let's take a look at the summation of 1 over n minus 0.5. What do you notice when you compare one over n minus 0.5 and 1 over n? Which is bigger? Yeah, 1 over n. One more time, which is bigger? One more guess?
1 over n.
One more guess?
1 over n minus 0.5?
Yeah, because look, n minus
yeah.
0.5 is a smaller number than n.
So yeah.
And you got to remember, if it's in the denominator, small and large switch. Okay, that's really important in this class. I mean, it's very basic math, but it's easy to not think about. Do you agree? I assume you all know that a bigger denominator makes the number smaller. Are y'all good with that?
Yeah.
Whoops, right there. There we go. So we know that's true. So if we look at the partial sum, for so the partial sums, there we go. For that guy, for the one we're interested, the summation of 1 over n minus 0.5 are all larger than the partial sums for the harmonic series. All right, well, if you're always bigger than the other guy, and the other guy goes to infinity, what must you go to? Yeah, it must diverge.
Infinity.
Yeah.
So therefore, the series summation of 1 over n minus 0.5 diverges. Any questions on the idea here? What I decided to do, because I had choices, what I decided to do is kind of prove by example instead of do a formal proof. The big theorem that's one of our two big theorems that's coming up. So we kind of see that there's really two cases. The first case is that if you have a series that's where the terms are always smaller than a recognizable series that converges, then you must converge. Okay, as long as you had to say positive, by the way. And if you have a series where the terms are always bigger than a recognizable series that diverges, then the original series diverges. There's nothing special about 0.5. If I put some other number in like 0.8, the same thing happens. Okay, all that we really used is the inequality. We use this big inequality with the greater than sign, and we use the fact that this guy diverged. We had to have that the terms are positive, at least large n. Who cares about small n? You never care about small n. For large n, then this works. So I'm going to generalize now with the big theorem. Now I want it to be big. And this is called the comparison test. And if you want to call it CT, you can. Just if you want to do some abbreviations, less writing if you want to. And it says the following. Consider the series the summation of a sub n such that we need to make sure they're positive. So a sub n needs to be greater than 0 for all n. Okay, and all n large is all we care about. Never care about the first million terms. All that matters is the tail. Okay, so then if the summation of Bn is another series with Bn greater than 0. Okay, pretty much this whole topic, you got to have positive numbers. Do you think we'll ever talk about negative numbers?
Eventually.
Yeah, Friday. So just let you know, give you a heads up, is that Friday we're back to negative numbers, okay? And we're going to do what's called alternating series, where you're going to have positive and negative alternating. Okay. No. Then if we have another series, there are two things that will help us. One is that if the summation of Bn converges and An is less than Bn, that was our first example. Any guess? What can we say?
It converges as well.
Yeah. Then the summation of An also converges. Okay, and what I'm going to do is I'm going to copy and paste number 1 into number 2. And what do you think I have to change? 3 things, sorry.
If EBN diverges.
Good. So I
And
don't want converges, I want diverges. What else do I have to change? I need the inequality to be the opposite. Whoops. So, and An is greater than Bn, then An also diverges. Okay, and the proof is basically the examples that I gave, except you do it in general instead of by example. But all the arguments are exactly the same. So I'm not going to do the formal proof, but if you saw the examples, that's basically the proof. Okay, and so this allows us to not have to do all of the explanation. Now we can just do these comparisons and say by the comparison test, and then it converges or diverges. Any questions at all on the theorem? Let me make it red. Any questions on this big theorem called the comparison test? And you are responsible for knowing the names of all the theorems. So we have 2 more today. Every day we have another, theorem or 2. We had 2 last time. Okay, maybe I'll do one more example and then you'll see how easy they are. Okay, let's suppose we want to look at, I'll do a really fun, easy super example. How about the summation of the fraction 1 over n to the 5th power times e to the n. And I'm not going to write down the question, I'll say it though. Does this converge or diverge? So any guess on what test we can use? What test can we use? Yeah, there's definitely going to be a comparison test. Maybe you could do integral test, but this would not be a fun integral to do. 1 over x to the 5th times e to the x dx. That's not a fun integral. I don't want to do that. And the interesting thing is, there's actually 2 good choices. Let's see if we can go with both of them. What are the 2 good choices? And they're both just as easy.
we could compare 1 over n to the 5th and then 1
test?
over e to the n.
Uh-huh.
Oh,
Okay, I think I'll do 1 over e to the n because that's different than what I did in the other example. But you could do 1 over n to the 5th if you want. I purposely gave this one so I can talk about both. So if you did 1 over n to the 5th, you do it using a p-series test. But I'm going to do it 1 over e to the n. So now, since that guy without the n to the 5th, does that converge or diverge?
Converges.
By what test?
The integral test.
There's an easier one. Integral test, you have a lot of work to do. Not p-series, it's not a p-series.
So divergence test.
No, it converges. Divergence never gives you converges.
Mm.
I purposely gave this one because it's been a week since you had this one. Starts with a G, that's a hint. Yeah, this is a geometric series test, right? Because this is a number to a power, right? Note that 1 over e is less than 1. And that's what you need. And if you want, I guess technically, that's a guide 1 over e, which is the same thing as 1 over e. Is less than 1, that's why it converges by the geometric series test. Any questions on that? And we also can say that this fraction, 1 over n to the 5th e to the n, is less than 1 over e to the n. Oh, sorry, 1 over, yeah, e to the n. Okay, and by the way, and everything's positive. You should always note that. You don't want negative anything, but there's no negative in anything in this example. Do y'all agree? But I didn't write down the word example. Yeah, now I'm happy. All right, so now, what can we say? Therefore,
It converges.
it converges, but you can't just stop. What else do you have to say? Yeah, by the CT, comparison test. Okay, you have to cite the test you're using, and notice that for this example, we needed 2 different tests, and that's common. Okay, we're done with just using one test. Now it's one test that'll allow you to use the other test and use the other test. You have to cite both of them. And I will take off points if you don't cite the test you're using. Okay.
I don't know if we've gotten this. I don't know if we'll get into this later on in the lecture, but will it eventually ask us a numerical value of where it converges?
Definitely not.
Okay.
Yeah, absolutely not. We're at the time where all we care about is, does it converge or diverge? And practically, that's important because if it converges, then you pop it in a computer. That's how you do things typically. There's a little bit more work to decide what your remainder is, and there are some remainder theorems, but we're not even going to do too much. We're only going to do a couple little remainder theorems. So usually just pop it into the computer, you throw in 1,000 or so, and you're happy. But the problem is that if it diverges and you pop it in a computer, you still get a number. Do you see the problem? And then you get tricked into thinking you have an answer, and you don't. And then you build that bridge, and then someone tries to go over the bridge and dies. and you killed someone. So, don't kill anyone. It's always better to check for convergence before you go and do it. Okay. Okay. Have there ever been any bridges that collapsed because someone didn't check for convergence?
I really hope not, but I'm sure there's been one.
The answer is yes. The Tacoma Narrows Bridge up in Washington. The good news is nobody was on it when it happened, but they have a film of it in the day when people didn't have smartphones. And it was because they didn't check for convergence, and you ended up with the divergent series, and then the bridge collapsed. Okay? And there's a really great movie on it. Okay, so this stuff really does happen in engineering. It's not just some math stuff. Okay, but I can't go over the hard physics to do that, or the hard math. Okay, so now I'm going to do another example. And this example is going to be disappointing. And here comes the next example. So let's suppose you have the series. And I'm going to make a fraction. 1 over n plus 4. Why is this one disappointing?
It's basically 1 over n.
Yeah, it looks like 1 over n. Let's use the comparison test. What's the problem? Yeah, less than 1 over n. It's a wrong inequality. Is that clear? So you can't use the comparison test. It does not work. Okay, so be careful about the comparison test. You can only use the comparison test if you have the right inequality. 1 over n diverges. This is smaller than infinity. Well, something smaller than infinity, well, it could be half of infinity, and then you still diverge. Or it could just be 3, and then you converge. Does that make sense? So the comparison test doesn't tell us anything. So let me write down the next theorem. This is called the limit comparison. And if you want LCT for a limit comparison test. So the idea of the limit comparison test is the following. You say, well, yeah, this is definitely smaller than 1 over n. But let's say n is 1 trillion. Are you going to notice the difference between 1 over 1,000,004,000,000 and 1 over 1,000,000,000,000?
No.
No, they're basically the same. In the limit, they're exactly the same. Do you agree? 1 over n plus 4 and 1 over n are the same functions for the limit as n goes to infinity. And that's what this limit comparison test is going to do, is that if the limits are the same, then we're going to be in good shape. Now, in terms of the same, I want to use their notation. Yeah, they do a n and bn. So we want to look at the summation, not of 1 over n to the 4th, but I'm going to copy it because it only changes a little bit, of an. Okay, so we have a series, the summation of an, and we're going to have a summation of bn. I should probably say let. And E sub n, B series, such that all terms are positive. We always want to look at positives. That helps. Okay, well, then what we're going to do, and let me make that red. So let's suppose that we have a series, and we have another series such that all terms are positive. What we're going to do is we're going to take the limit of an over bn, and we're going to see what happens. Okay, so let's suppose that the limit, make it a pretty limit, the limit of an over bn is a nice number, not just any nice number. We want it to not be 0. Because if it's 0, then that tells you that they're really not similar, an and bn. Okay, we want them to be similar.
So we want it to approach 1.
No, it could approach 7, that's fine. But not 0. So let's suppose we take the limit and we get a number, not infinity, not 0. Okay, then the limits converge or diverge together, the series converge or diverge together. What that means is that if an converges, bn converges. If an diverges, bn diverges, and vice versa. Any questions on the first part of the theorem? All right, now let me copy and paste. All right, well, limit could not, one possibility is limit's not 0. What's another possibility?
It doesn't exist.
It does exist, okay. But if it doesn't exist, it's a special not exist. I think I want to do Victor's idea first, though. We will get to yours. And that is, it could be equal to 0. So suppose the limit is 0. And let's take a look at this. So if the limit is 0, that means that an is smaller than bn. Do you agree? So if the limit is 0, then an is smaller than bn. Bn is the bigger guy. So if bn converges, then an better converge. So let me fix this. Then if bn converges, so does an, the summation of an. Any questions on that? Okay, so if the limit's 0 and bn diverges, that means we know nothing. So that means this test didn't work. And that happens a lot. You don't know anything. Okay, okay, well, the other thing is we could have, instead of being equal to 0, we could have it being equal to, what's the last little thing? Is infinity. Those are the 3 choices. You can not 0, be 0, or be infinity. Then if bn, so now let's take a look at it. So that tells us an is bigger than bn, a lot bigger than bn, for that limit to give you infinity, right? So now if the summation of bn diverges, okay, so that the b's, if the b's are big and a's are even bigger, then The A's must diverge also. Okay, now this is not all possibilities as Ralph looked at, because if the limit is 0 and Bn diverges, you just frown. That means you compared with something that didn't help. Okay, not everything is going to work. Okay, so you have to look at it, and usually you try and find something similar. Any questions on that? So let's do an example. Okay, and I'm not going to write the question. The question is always decide if the series converges or diverges. So let's grab a series. So let's suppose you have a summation of how about n squared minus 2n plus 3 divided by n cubed plus n minus 7. And we want to decide if this converges or diverges. Any questions on the question? All right, so you look at this, and what you do is you say, what does this look like in the limit? Can I make this a lot simpler, and it'll be basically the same idea. It'll be slightly off, but not by much.
Yeah, you could look at n squared over n cubed.
Yeah, but even better, what's n squared over n cubed?
1 over n.
1 over n.
Yeah, we can look at the harmonic series. So we can look at the harmonic series. So let Bn actually, let me go summation of Bn equal the harmonic series. So summation of 1 over n. This diverges by the harmonic series test. It is a harmonic series. Any questions on that? Okay, you could try to see, well, maybe it's bigger, but it doesn't look bigger, does it?
No.
Okay, it's actually smaller, but not by much. So we can't use the comparison test, but we can use the limit comparison test. So to do the limit comparison test, what I'm going to do is I'm going to take a limit. And then I'm going to look at the fraction. An over Bn. Any questions on that? Okay, well, I think you all know how to divide fractions. You better. So that is equal to the limit of n cubed minus 2n plus 3 over n cubed plus n plus 7. Something I didn't mention, and I hope it's obvious to everyone, is that these are all positive for large n. There's no problem with the positive negative thing. You should always check that. What is that limit? There's an easy limit at the hint. What do you get when you take the limit as n goes to infinity of that fraction?
Infinity over infinity.
Yep, but what do you get finally when you do all the work? But you should be able to do it in your head, hopefully. Just look at the dominant terms, it basically is all you have to do. It's a very easy answer.
1.
1. Okay, just L'Hopital's rule 3 times. The n cubed is all that's left, and you're going to get the same third. You're going to get the same third derivative for the n cubed. The others go away. Okay, so that's just 1. So what can we conclude?
It converges.
Yeah, and it's by the limit comparison test. Okay, again, you have to state the theorem or I will take off points. The series. And the word it is a little ambiguous because we have 2 series over here. The series we're interested in. So I'm just going to copy and paste it. One of the nice things about taking your test on the computer is you can copy and paste also. It makes life a lot faster. And that's it. It converged. And that wasn't too hard, was it? Imagine if you had to do the integral test on this sucker. Good luck. That would not be fun at all. But this was not too bad. Okay, so let me give you the strategy. Okay, so when you're talking about a series like what we just did, the first thing you do is you say, what does it look like? What are the dominant features of this series? Any questions on that? And in this case, the dominant features are n squared and n cubed, and that reduces to 1 over n. Then you say, well, is there an obvious inequality? And in this one, there's no obvious inequality. Okay, it's actually, to me, it's obviously the wrong inequality. But if you have to work hard on the inequality, don't go and do a limit test, a comparison test. Do the limit comparison test. So then you have to state whether the one you're comparing with converges or diverges. Okay, and in this case, it diverged by the harmonic series test. Then you take the limit, and pretty much all the time, you're going to be using number 1. If you're not using number 1, you probably guessed wrong on what the series looks like. Okay, because if you just look at the dominant terms, you're always going to get a nice limit. I'll let you know that. So in this case, we got the dominant term, and we end up with a limit of 1. And once you get a limit as 1, you say by the limit comparison test, and you just repeat whatever you had for the first series. Diverges in this. Oh, sorry, I wrote converges. This is diverges. Because the first diverged. Sorry about that. So whatever this says over here, you get the same answer down here. There are, a few rare cases of using number 2 and 3, but if you do things right, it'll always be number 1. Does this test always work? What do you think?
No.
No. When does it not work? Here's the hint. Read the first sentence.
When there's negatives involved.
When there's negatives involved. And if there's negatives involved, you wait 48 hours. How come?
Friday.
Yeah, that's Friday. Friday, we're dealing with negatives. Okay, we haven't touched negatives yet. Friday, we get to do with negatives. And we're going to find out that things are different if you have negatives involved. But as long as everything's positive, limit comparison test is very powerful. And it's the main test to use. But notice that you use it with another test. because you got to use another test for the simpler series. And that's real common. I'm looking at my clock. It's 11:15. So just right. So I'm going to stop share, stop the recording. 15.